This is the Edexcel A-level Maths 2022 Paper 2, Pure Paper 2. Question 1. So it says, you must show all stages of working and solutions relying entirely on calculator technology are not acceptable. Basically, if you have a graphical calculator, great, but if you just key this into your graphical calculator and report the answer, you're not going to get any marks. Okay, so we've got a sketch of mod 3 minus 2x. And we need to solve mod 3 minus 2x equals 7 plus x. Well, it's very helpful they've drawn this for us. We can use that. So that bit is already on the graph. I'm going to add a graph of y equals 7 plus x. So 7 plus x has a y-intercept of 7. Now I know that's above this point because this is the y-intercept of 3 minus 2x modded, which is when x is 0, which is 3. So 7 is above that point. Now, 3 minus 2x has a gradient of minus 2, that's this one, and the kind of modded bit, this bit, has a gradient of 2. So 7 plus x has a gradient of 1, so I'll draw my line with a gradient which is clearly less steep than the mod graph there. That's important, otherwise you won't get this solution here. Okay, there's going to be two solutions, one here and one here. So imagine that the modulus sign was not there. 3 minus 2x, that's this bit of the graph here. This bit is just 3 minus 2x, or at least a section of it. This part over here is where the mod has kicked in and multiplied it by minus 1. So this bit over here is a section of y equals minus 3 plus 2x. I can find these two solutions simply by finding where 7 plus x intersects with each of these bits. So this one over here will be where 3 minus 2x equals 7 plus x. I can add 2x to both sides. I can subtract 7 from both sides. And I get x equals minus 4/3. And that looks about right. I mean, looking is not proving, but at least I was expecting a negative answer there. This solution here will be where the sort of negative bit, the bit that's been modded, which is minus 3 plus 2x, intersects with 7 plus x. I can subtract x from both sides, add 3 to both sides, and there are my two solutions. X is minus 4/3 and x equals 10. Notice they did not say find the coordinates. So I don't need to bother with y values. They just said solve this equation, which is just x's. So there's question 1. Question 2, sketch the curve with equation y equals 4 to the power of x, stating any points of intersection with the coordinate axes. Okay, so this is an exponential graph. So all exponential graphs that have a base that's above 1 have a similar shape. You know what, I can do better axes than that. If I was doing this with pen and paper, I would use a ruler for this just to make it really neat. So it tends towards the x-axis there, it creeps up, it creeps up, it creeps up, and then it just goes up, 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 up. So that's y equals 4 to the x. The points of intersection, there's only one point and it's here. That's when x is 0 and 4 to the power of 0 is 1. So that's x equals 0 and y equals 1. And I think that's that for that part. Okay, part B. Solve 4 to the x equals 100, giving your answer to 2 decimal places. While this one's pretty easy, we can just use logs. 4 to the x equals 100. I would just use log base 4 here. No need to mess around with any other bases. Log base 4 of 100. And we can just do that here. So log base 4 of 100. And it's 3.32. Just check how the 2 decimal places. So x is 3.32. And we're done. Question 3. A sequence of terms A1, A2, A3 and so on is defined using this. Okay, so we've got a term by term definition here, recurrence relation. Show the sequence is periodic. That means it repeats. So let's just work out a few terms. The first term is 3. The next term is 8 minus the previous term, which is 5. The next term is 8 minus the previous term, which is 3. And we've got repetition, right? It's just going 3, 5, 3, 5, and so on. Now, it says state the order of this periodic sequence. That is simply how many terms there are within each repetition. So there's 2 terms within each repetition. So the order is 2. Find the value of, now what is that? That's the sum from n equals 1 to 85. It's the sum of the first 85 terms. So we can't use any formula that we know. This is not an arithmetic or geometric sequence. So we've got to use a bit of logic here. This is going to repeat ... in 2s all the way up to the 84th term. So up to here, you've got 84 terms, right? 84 is an even number, so that gets me up to this. And then there'll be one more 3. So this section here has 84 terms, and therefore it's got 42 pairs. So 42 pairs, each of those pairs has a 3 in it and a 5 in it. And then there's one more 3 at the end. So we can just work out 42 times 8 and add 3, and it's 339. I just wanted to tell you really quickly about my website, where I have a complete online course covering the full A-level syllabus made up of hundreds of videos, quizzes and worksheets. If you're finding this useful, please check it out using the link in the description, and the first 100 people to use the promo code can get 30% off. Right, back to the paper. Question 4. Given that y is 2x squared, use differentiation from first principles to show that dy by dx is 4x. So you want to imagine a section of the curve here, and imagine 2 points on it. This point here can be the point with an x-coordinate of x and a y-coordinate. Well, it's y equals 2x squared, so the y-coordinate is 2x squared. Then you're going to imagine another point a little way along. Its x-coordinate is x plus a little bit. Now, people use delta or h. I'm using delta. Kind of looks more pro, and that's 2 times x plus delta all squared. Now, the definition of the derivative is the limit as delta tends to 0 of the gradient of the chord between those 2 points. So what we can say is that dy by dx is the limit as delta tends to 0 of change in y over change in x, which is simply 2x plus delta squared minus 2x squared, that's the change in y, divided by the change in x, which is x plus delta minus x. Now we just need to simplify all of this before sending delta to 0. So it's the limit as delta tends to 0. Well, I'll just expand all of this. So when I expand this bracket in here, I get x squared. So that's going to be 2x squared. I also get 2x delta. So that's 4x delta. I get delta squared. So 2 delta squared. Then minus 2x squared. And on the denominator, the x's cancel and it's just delta. So we have the limit as delta tends to 0. Well, we can really simplify this now because the 2x squared minus the 2x squared cancel, and I can divide top and bottom by delta. So it's gone from the bottom, and on the top it's 4x plus 2 delta. Now that I don't have a delta in the denominator, I can evaluate what the limit is as delta goes to 0. When delta goes to 0, that is just 4x. And there we go. We've shown from first principles that the derivative of 2x squared is 4x. Question 5. The table below shows corresponding values of x and y for y equals log base 3 of 2x. The values of y are given to 2 decimal places as appropriate. using the trapezium rule with all the values of y in the table, find an estimate for this integral. Okay, so the trapezium rule gives us a way to approximate integrals, and the formula for that, well, we can just say that this integral is going to be approximately, and the formula, recall, is h over 2, where h is the gap between each of the points, and it's the first y value, so y naught, plus the last y value, yn, plus 2 times all the others, so that's y1 plus everything up to yn minus 1. All right, what is that? Well, h is the size of the gaps, which is 1.5. So we've got 1.5 over 2, and then it's the first y value, y0, which is 1.63, plus the last y value, which is 2.63, plus 2 times everything in between, which is 2, plus 2.26, plus 2.46. We can then just key that whole lot into our calculator, and when we do that, we get 13.275. Now, what I quite like to do in those sorts of questions is just check it by using the calculator's integration function. This should be pretty close to the correct answer. So I can do that by just saying what is the actual answer, or at least a more accurate one, log base 3 of 2x between 3 and 9. And yeah, it's pretty similar, 13.32 as opposed to 13.275. So it should be quite close. If it was miles off, you'd know you'd probably made a mistake. Okay, using your answer to part A and making your methods clear, estimate these. So you're going to need to think about what is the connection between this and these. So for part B1, we can say that this here, well, we can use the log rule, that log base 3 of 2x to the power of 10, we can bring that 10 down to the front. In fact, we can then move it outside the integral, so it's just 10 times the integral from 3 to 9 of log base 3 of 2x. And we've just evaluated that, so it's 10 times 13.275. So that's easy enough. That's just 132.75. For part 2, well, what's the connection here? Log base 3 of 18x between 3 and 9 again. Well, we can use a different log rule here. Now, we very much want to express that in terms of log base 3 of 2x, which is the thing we know about. So notice the log rule, which says, the addition rule, says that's the same as log base 3 of 2x plus log base 3 of 9. Because remember, 2 logs added together, you can just multiply the subjects, giving you the 18x. So if we split this up now, we can say that's the integral from 3 to 9 of log base 3 of 2x, which is the thing we already know, plus the integral from 3 to 9 of, well, what is this? This is log base 3 of 9. Well, that's just 2, right? 3 squared is 9. So that's just simply the integral of 2. Okay, each of these at a time. This one we know, it's just 13.275. What's this? Well, the integral of 2, you could imagine a graph of this. That's just y equals 2, right? That's just this. And we want to evaluate that between 3 and 9. Well, that's just a rectangle with a base of 6, and a height of 2, so that's 12. So we can add these together and we get 25.275. Again, you can do a quick check of that quite nicely using the calculator by just saying, change that to 18, not that, this to 18. And yeah, look, it's really similar. Again, if you'd made a mistake, that would be miles off. So there is question 5. Question 6, figure 2 shows a sketch of part of the curve with equation y equals f of x, and f of x is 8 sine half x minus 3x plus 9, and it's only for positive x values. X is measured in radians. The point P, shown in figure 2, is a local maximum point on the curve. Using calculus and the sketch in figure 2, find the x-coordinate of P, giving your answer to 3 significant figures. Well, to find stationary points, we differentiate and set it to 0. Now, when I do that, I'll find all stationary points. The first one, theoretically, would be this. The next stationary point would be this one, and the third one is P. So I need to find the third smallest positive x value that's a stationary point. So I'm going to differentiate that and set it equal to 0. So f dash of x is, we're using the chain rule, and differentiate sine, I get cos, but the half here means I need to multiply by a half. So I get 4 cos half x. Differentiate negative 3x and it's minus 3. Differentiate 9 and I get 0. So here's what I'm solving. So we get 4 cos half x equals 3, and cos of half x equals 3/4. So that means that half x is inverse cos of 3/4, and I want the third solution to this. So when you do inverse cos of 3/4, you need to make sure your calculator is set in radians. Inverse cos of 3/4 is 0.7227. The next solution for cos is always 2 pi minus your previous answer. So that's 5.560. Now, your next one is just going to be your original first answer plus 2 pi, because the cos graph has a period of 2 pi. So that's 7.006. To find x, we just need to double these, but I'm not interested in that one or that one. I'm interested in this, which I will double to get 14.01. Now I'll just check how they wanted that. 3 significant figures, well, it's 14.0. Okay, part B. So part B says the curve crosses the x-axis at x equals alpha. That's here. Given that to 3 decimal places, f of 4 is 4.3 and f of 5 is minus 1.2. Explain why alpha must lie in the interval 4 to 5. The idea here is when you chuck in 4, you get something positive. When you chuck in 5, you get something negative. Well, how do you get from positive to negative on a continuous function? Well, you must cross the x-axis at some point. So we just need to explain that. And the wording here is important. So we can say that since f of 4 is positive and f of 5 is negative, and that it's a continuous function. That's really important, because if there was an asymptote, that this wouldn't follow. Since this one's positive and this is negative, and f of x is continuous, alpha lies in the interval 4 to 5. Part C. Taking x naught equals 5, use as a first approximation to alpha, apply Newton-Raphson method once to obtain f of x to f of x to obtain a second approximation to alpha. Show your method and give your answer to 3 significant figures. So Newton-Raphson formula is that the next best approximation is your previous approximation minus f of the previous approximation over f dash of the previous approximation. So for us, our x naught was 5. So it's going to be 5 minus, and it's f of 5, so that's 8 sine of half of 5, so 2.5, minus 3 times 5 plus 9, because that was the formula here, divided by the derivative at 5. And we've already differentiated above, and the derivative was 4 cos half x, so 4 cos 2.5 minus 3. And you really can just key this all into your calculator. And when I do that, I get 4.80 to 3 significant figures. Okay, question 7. Find the first 4 terms in ascending powers of x of the binomial expansion of this. Okay, so it's a binomial expansion where n is a fraction. So what we have is 4 minus 9x to the half. To do this expansion, you need a 1 here. That's how we use this. So to do that, I can factorize out 4. I can say that this is 4 times 1 minus 9 over 4x, and all of this to the half. 4 to the half and this to the half. Well, 4 to the half is 2, and I can use the binomial formula for this. So the binomial formula says that the expansion of 1 plus a term, right, ax, all to the power of n, is 1 plus nx. So it's plus n, well not n, x, n times ax. So it's n times all of this, plus n times n minus 1. So half times half minus 1, which is minus a half, multiplied by my ax term squared over 2. I didn't give myself enough room here, so I'll keep going here, plus n times n minus 1 times n minus 2 times my ax term, minus 9 over 4x cubed, all over 3 factorial, which is 6. Okay, there's the first 4 terms. Now I just need each of these in its simplest form, and I can definitely use my calculator to help here. So the first one's easy. 2 times 1 is 2. The next one, 2, well, it cancels with a half. That's nice. So that one I can do without the calculator. So minus 9 over 4x. Next one, absolutely just going to key into the calculator. What have we got? We've got 2 times a half. I know that's just 1, but forgive me. Times minus a half times. And I'm quite a big fan of just keying this in as you see it so that you don't make any errors, right? You can have as many of these fractiony bits as you like just to ensure you don't make any errors. So it's that term squared. I'll remember there's an x squared in there as well. So that term there is minus 81 over 64. So you've got minus 81 over 64 x squared. And for the last one, I can actually just adapt it because I still have the 2 at the front. I've still got the half. I've still got the minus a half. I also want times by minus 3 over 2. It's now this term up here cubed, and it's over 3 factorial, which is 6. And it's that. So minus 729 over 512. And that's x cubed. So quite a lot of number crunching in that question. All right, so this one looks like you're going to have to be subbing things in or anything, but they tell you don't do any calculations. What you have to notice is that all future terms of this expansion will be negative because look at the difference between this one and this one. What happened was I multiplied by another negative number, and then I multiplied by minus 9 over 4x again, right? Because it was squared and it went cubed. If I was to do the next term, I'd be multiplying by another negative number, right? N minus 3. This was n minus 1, n minus 2, n minus 3. So I'll be multiplying by another negative number, and then I'll be multiplying by minus 9 over 4x again. What it means is every single coefficient after the first one is negative. So it means that if I stop at any point, my answer will always be a bit bigger than the real answer. The real answer would be if you continued this forever, keeping, subtracting more and more little bits. So you can say that if you stop at any point, which we have done, it's an overestimate. Since all terms after the first are negative. So pay attention when they tell you not to do any calculating, because you could waste a lot of time subbing 1/9 into this. Okay, question 8. Figure 3 shows a sketch of part of the curve with equation y equals x minus 2, x minus 4 over 4 root x. The region R, shown shaded in figure 3, is bounded by the curve and the x-axis. Find the exact area. Okay, so we're going to use integration here, but we'll need to know our limits. Our limits are the roots of the equation. So the first thing I can do is just find, or really just state the roots. When does this equal 0? Well, any fraction only ever equals 0 when the numerator is 0. So that's when x minus 2, x minus 4 equals 0. So therefore our limits are x equals 2 and x equals 4. So we're looking for the integral between 2 and 4 of this function. Now, this is an area of a region below the x-axis, so I know that this integral will be negative, and I'll just remember to multiply by minus 1 at the end. I'm also going to expand this because it's going to be much easier to integrate if I do that. So we get x squared minus 6x plus 8 all over 4, and I'm going to write this as x to the half. You'll see why in a moment. That 4, I'm happy to just pull out as a quarter here. That's going to make my life easier. X squared divided by x to the half is x to the 3 over 2, because I'm subtracting powers. Now 6x divided by x to the half is just 6x to the half. And finally 8 over x to the half is 8x to the minus half. Now I do the integration, raise the power by 1, divide by the new power, raise the power up to 3 over 2 and divide by that, so that's multiplying by 2/3, so we get minus 4x to the 3 over 2. Raise the power up by 1 up to a half and divide by that, so plus 16x to the half. And I'll be evaluating this between 4 and 2. Subbing in 4, I get a quarter of, and this bit you want to show for method marks that you're subbing these things in, but I probably would evaluate each of these with a calculator. Let me show you. So it's 2/5 times 4 to the 5 over 2 minus 4 times 4 to the 3 over 2 plus 16 times 4 to the half. So I'm showing that I'm subbing it in and mopping up all of the method marks. Minus a quarter of, and now I'm subbing in 2. So 2/5 times 2 to the 5 over 2 minus 4 times 2 to the 3 over 2 plus 16 times 2 to the half. Now here's what I mean by subbing this into the calculator. I'm just going to show the answer to each of these sections. So for a quarter times, and all of this I'll just be subbing in now. So we have 2/5 times 4 to the power of 5 over 2, which is 2.5, minus 4 times 4 to the power of 3 over 2, which is 1.5, plus 16 times 4 to the half. And that turns out to be a nice number, so that's 64 over 5. Okay, then for the 2, I subtract a quarter times, and now I can just go back to my calculator and I can just edit it all and change all of the 4s to a 2. And when I do that, I get 48 root 2 over 5. Okay, let's tidy this up. So we had 64 over 5, and then that's times a quarter. Well, that gets me 16 over 5. And then for this bit here, well, the quarter can multiply by the 48 to give 12 root 2 over 5. We're almost done. We just need to remember that that was a negative number since this was below the axis. So that, and you can check if you like, if you actually just compute that, you'll see it's minus something. It's minus 0.194. So the actual area is this times minus 1. So you can just flip it round. So 12 root 2 over 5 minus 16 over 5. Now this is a nice question to check. Here's how. You can just key the original problem in as an integral. This is just a check. You're not going to get any marks for this, but in the heat of the exam, it can be quite nice to know you've got a question correct. So I'm just keying this in as I see it for root x between 2 and 4. So it's minus 0.194. And if you just check that by keying it into your calculator, well, if you check this, you'll see it's exactly minus 0.194. And it just proves that we're correct. Okay, question 9. Figure 4 shows a sketch of a Ferris wheel. The height above the ground, h meters, of a passenger on the Ferris wheel, t seconds after the wheel starts turning, is modelled by the equation h equals a sine bt plus alpha. A, b, and alpha are constants. Figure 5 shows a sketch of the graph of h against t for one revolution of the wheel. Oh, and it's the modulus of all of that. Given that the maximum height of the passenger above the ground is 50 meters, so this bit up here is 50, the passenger is 1 meter above the ground when the wheel starts turning, so that's this point here is 1, and I'll maybe just mark that on here. This point up here is 50. The wheel takes 720 seconds to complete one revolution. So that's going to be this here is 720. Find a complete equation for the model giving the exact value of A, the exact value of B, and the value of alpha to 3 significant figures. Okay, this is quite a lot going on here. We're going to need to use some facts about trig graphs here to do this. So this, if you forget about the modulus for a moment, this is a standard sine curve. Okay. Now, sine curves exist between -1 and 1. I just realised I wrote 5 here. It should be 50. Now, this one doesn't go up to 1, it goes up to 50. That means that our A must be 50, so that one we can just state. Okay, now what about the B here? Well, a normal sine graph, if I was to just do a little sketch of it here, would complete a full period in 360 degrees. Now, this is not actually a transformation of a full period. It's a transformation of the period from 0 up to some point here, right, with this bit there being the modulus bit coming up like that. So it looks to me, oh yeah, since it also starts here and finishes here, so that's half of a complete cycle. Now, half of a sine cycle would normally be 180 degrees, but this took 720, which is 4 times bigger. So the sine curve, the standard sine curve, has been stretched out by a factor of 4. That means that b must be a quarter because of the f of kx is actually a stretch of 1 over k. So if k is a quarter, it stretches it out by 4, and if b is a quarter, it stretches it out by 4 as well. So our little b must be a quarter. Now, to figure out what the alpha is, it's probably easiest to just sub in a point that we know, and the easiest point we know is just t is 0, h is 1. So I can say that the height is 1, and that's the modulus of, well, a is 50, sine of, well, when t is 0, that's just 0, so it's just sine alpha. So I can just solve this now. Now, the modulus of 50 is just 50, so I can divide both sides by 50. So I have 1 over 50 equals sine alpha. I don't need to worry about it being negative because it's not negative, and that's in the first part of the sine graph. So I just do inverse sine of 1 over 50, and I get alpha is 1.1, how much? 3 significant figures, so 1.15. Okay, part B, explain why an equation of the form h equals mod, well, the same stuff as before, plus d, where d is a positive constant, would be a more appropriate model. So what's the difference? Well, the original model, which didn't have the d, did actually hit 0 here. Now, why is it unlikely that their height above the ground isn't actually 0? If it was 0, they'd be basically scraping the ground. Now, in the image, it looks like they actually don't. So probably say something like, the passengers do not touch the ground when they go round. Whereas if we look at the original function, which was when h was equal to mod a sine bt plus alpha, it suggests they do touch the ground. So I think that's a reason why that model is more appropriate. Question 10. f of x is 8x plus 5 over 2x plus 3. X is always greater than minus 3 over 2. Find inverse f of 3 over 2. Now, we don't actually need to find the inverse function of this to solve this question. We could, but we don't need to. It's actually easiest to just solve 8x plus 5 over 2x plus 3 equals 3 over 2, right? Because that's basically setting f of x equal to 3 over 2, and therefore x is going to be the inverse of 3 over 2. So I can just solve this. 8x plus 5 is, well, 2x times 3 over 2 is 3x, and 3 times 3 over 2 is 9 over 2. Subtract 3x from both sides, you get 5x. Subtract 5 from both sides, and you get minus a half. And so x is minus 1 over 10. You can always check this by just subbing in minus 1 over 10 into here and checking you do get 3 over 2. Okay, show that f of x is equal to that, a plus b over 2x plus 3, where a and b are constants. So I think quite a nice way of doing this, I find, is to try to make the top a multiple of the bottom. So the bottom is 2x plus 3. The 8x here, well, that's 4 times the 2x. If only if it were 8x plus 12, then the top would be the an exact multiple of the bottom. So what you can do is 8x plus 12 over 2x plus 3, and then think, how do you need to correct this to get to the number that it actually is? Well, you just subtract 7. 12 minus 7 is 5. So what we now have is 8x plus 12 over 2x plus 3 minus 7 over 2x plus 3. This is nice because that is simply 4. So we have 4 minus 7 over 2x plus 3. And we've done what we were asked, which is to express it in the form a something plus something over 2x plus 3. Our a was 4, our b was minus 7. Okay, the function g is defined to be 16 minus x squared, and x exists only between 0 and 4. State the range of the inverse of g. Okay, to do this, I'd remember or recall that the range of the inverse is the same as the domain of the function. So it's just 0 to 4. So I don't really need to do any work there to say that the inverse of g exists in the same values as the domain of the original function. Find the range of f of g inverse of x. Okay, well, I know that the range of the inverse of g is 0 to 4. So that's the kind of what's coming out of the function g inverse. If I now apply my f function to that, I want to know what numbers come out of that. So it's basically like considering the original function. And by the way, we've been prompted to look at this, so I might think that could be significant here. So what happens when I put numbers 0 to 4 into this function? So if I'm only putting in x values between 0 and 4 into this, what do I get? Well, it's a useful thing to have a sketch of this. The reason is you've got an asymptote, you've got a bunch of stuff going on. Now, the asymptote of this is at minus 3 over 2. Now, luckily, that's not in our range here. So what do these sorts of graphs look like? They look like reciprocals. Like sometimes they look like this, sometimes they look like this. The point is, this asymptote here is not in our function in this range. So we have a continuous function in this range. Now, one property of these sorts of reciprocal functions is that they're always increasing or always decreasing. So I actually don't need to stress about there being maximum or minimum points to kind of spoil what happens here. I can actually figure out what the minimum and maximum points are by just subbing in 0 and 4. So when I do 4 minus 7 over 2 times 0 plus 3, I get 4 minus 7 thirds, which is 5 thirds. And when I evaluate 4 minus 7 over 2 times 4, which is 8 plus 3, I get 4 minus 7 elevenths, which is 37 over 11. So what I've discovered is that the smallest value of this in this range is 5 thirds, and the largest value is 37 over 11. So I know that f of g inverse exists between 5 over 3 and 37 over 11. Question 11. Prove using algebra that n times n squared plus 5 is even for all n. All right, so how are we going to approach this? Well, probably a useful way of approaching it is to think about whether n is even or odd. Because clearly, if n is even, then this expression is even. If n is odd, then that bit's odd, but what we've got is an odd square plus 5, which is going to be even. So basically, either n or n squared plus 5 is always even. And I just need to show this when n is even and when n is odd. So if n is even, we can say that n is just 2 times something. Let's say 2m, where m is an integer. Well, in that case, n times n squared plus 5 is 2m times 2m squared, so 4m squared plus 5, and that's even because it's 2 times something. Now we can say if n is odd, then we can say that n would be 2 times m plus something, again for m as an integer. So then we can say that n times n squared plus 5 is 2m plus 1 times, okay, it's n squared, so it's this thing squared. When I square that, I get 4m squared plus 4m plus 1, and it's all of that plus 5. Why is this even? Well, that second bracket is actually all made up of even numbers. It's 4m squared plus 4m plus 6. Pull out a 2 from that to hammer home the point. It's 2 times 2m plus 1, 2m squared plus 2m plus 3, which is even. So what we've shown is if n is even, the expression is even, and if n is odd, the expression is even. Question 12. The function f is defined by f of x equals e to the 3x over 4x squared plus k. K is some positive constant. Show that f dash of x is all of that. So I'm going to use the quotient rule for that. I'm going to call the top u, e to the 3x, and find that u dash is 3e to the 3x. V, the denominator, is 4x squared plus k, and v dash is 8x. So the derivative, f dash of x, using the quotient rule, is v u dash, so it's v u dash minus uv dash, so that's 8x e to the 3x, all over v squared, and that's 4x squared plus k all squared. Okay, I need to simplify this. How am I going to do that? Well, I'll probably factorize out e to the 3x on top. So e to the 3x, and what's left? Well, you've got 3 times all of this, so that's 12x squared plus 3k, and you've got minus 8 times this, so minus 8x. All of that over 4x squared plus k all squared. So, do we have it in the form they want? Yes, because it's 12x squared minus 8x plus 3k times g of x, and g of x is just all that's left. So I can just write it out exactly as they've got it, 12x squared minus 8x plus 3k multiplied by e to the 3x over 4x squared plus k all squared. So there's that bit, and there's the g of x. Okay, given that the curve with equation f of x has at least one stationary point, find the range of possible values of k. So stationary points occur when the derivative, this, is 0. Notice that this bit over here is never 0. E to the 3x is never 0, and 4x squared plus k all squared can't be 0. Well, and that's almost irrelevant. I mean, it's a denominator, so it doesn't matter. This isn't 0 because e to the 3x is not 0. So it's only going to be a stationary point when this bit is 0. So what do we know? We know that stationary points occur when this equation is true. They've told us that there is at least one stationary point, so this must have at least one solution, has at least one solution. Now that's just a quadratic. Quadratics with at least one solution have the property that their discriminant, b squared minus 4ac, is greater than or equal to 0. If it's greater than 0, it's got two solutions. If it's equal, it's got one. So b squared, that's negative 8 squared, minus 4 times a times c. That must be greater than or equal to 0. Solve this, 64 minus, 4 times 12 times 3, that's 144. K should be greater than or equal to 0. So 64 is greater than or equal to 144k, and divide 64 by 144, we get that k is less than or equal to 49. But take a look here. It also says that k is a positive constant, so it's not just that, it's also that k is greater than 0. Question 13. Relative to a fixed origin O, the point A has position vector that, the point B has position vector that, the point C has position vector that, there's a P in there. P is a constant. Given that A, B, C lie on a straight line, find the value of P. Well, if they lie on a straight line, then the vector from A to B is going to be parallel to the vector from B to C. So I would just say, what is A to B? Well, it's B minus C. So I prefer to do this in columns. I find it a bit easier. So it's 0i, 4j, 6k, minus A, which is 4 minus 3, 5. And we get negative 4. 4 minus minus 3 is 7. 6 minus 5 is 1. Now, what do we get when we do B to C? It's the position vector of C, minus 16, P, 10, minus the position vector of B, which is 0, 4, 6. That gives us minus 16, P minus 4, and 4. Now, if these two things are parallel, this should be a multiple of that. So that should be some constant k times minus 4, 7, 1. Well, you can clearly see that k has to be 4 to make minus 4 times 4 is minus 16, and 1 times 4 is 4. So k is 4, and that means that p minus 4 better be 4 times 7, which is 28. 28 plus 4 is 32, and we found what P is. So next, the line segment OB is extended to the point D, so that CD is parallel to OA. Find the modulus of OD. Right, we've got 3 points in a line here. Let's just draw them out. So you've got point A, B, and C. And let's put an origin in somewhere. It doesn't really matter where. And what have we been told? We've been told that the line segment OB is extended to the point D. So it will be extended some way along here, so that CD is parallel to OA. Well, OA is that. So we want CD to be parallel to that. So that suggests that D is about here. Find the modulus of OD. So let's actually try to work out what the point D is. Well, we know that to get from O to D, you just do O to B, but multiplied by something, OB times something, let's call it lambda. So what is OB? OB is some multiple of 4j, OB is 4j plus 6k. So what we can say is since OB is 0, 4, 6, O to D must be 0 and then 4 times something, let's call it lambda, and 6 times that same value. Now what we can do is insist that O to A is parallel to CD. Well, what is O to A? O to A is just 4 minus 3, 5. So O to A is 4 minus 3, 5. What is C to D? Well, C to D is the coordinates of D, or the position vector of D, which is, so C to D is the position vector of D, which is 0, 4 lambda, 6 lambda, minus the position vector of C, which is minus 16, P, which we know, 32, 10. So minus 16, 32, 10. So we can just get an expression for that. It's 0 minus minus 16, which is 16. It's 4 lambda minus 32, and it's 6 lambda minus 10. So these two things, OA and CD, are supposed to be parallel. What does that mean? It means that this is a multiple of that. Now, they want the modulus of OD. So if we can work out what lambda is, we should be able to do it. So what do we know? We know that 16, 4 lambda minus 32, 6 lambda minus 10 is some multiple. I guess I won't use K, I'll use any other. I'll use M of 4 minus 3, 5. So we can see just from the I coordinate that M has to be 4. Okay, let's just check that these other ones check out. What we'll then have is that 4 lambda minus 32 equals 4 times negative 3s. Well, what would that imply? That would imply that 4 lambda is negative 12 plus 32, which is 20. It would imply that lambda is 5. Let's just check that works for the K coordinate as well. We would also have that 6 lambda minus 10 equals M, which is 4 times 5, which is 20. That would mean that 6 lambda is 30, dividing through by 6. Okay, good. So if that didn't work, it would mean, if we hadn't got the same answer, it would have meant that we must have made a mistake, basically. Okay, so we now know that lambda is 5, and we can work out, therefore, what the modulus of OD is. Remember, the position vector of OD was this, 0, 4 lambda, 6 lambda. Since lambda is 5, OD is 0, 4 lambda, that's 20, 6 lambda, 30. So the modulus of OD is the square root of 0 squared plus 20 squared plus 30 squared. Key all of that into the calculator, or do it in your head if you're a whiz with that sort of thing. We end up with 10 root 13. Question 14. Express 3 over 2x minus 1, x plus 1 in partial fractions. Okay, so it's 3 over 2x plus 1, 2x minus 1, x plus 1. So if we express this in partial fractions, it will be something over 2x minus 1 plus something over x plus 1. multiply, let's use 3 because it's an equivalence here. Let's multiply this out, or add these fractions rather. We get a x plus 1 plus b 2x minus 1. The denominator would be the same. I can see that the denominator will be the same on both sides, and so the numerators are equivalent. Now I like to use substitution here, so sub in x equals minus 1. That will make this disappear, so we've got 3 is equal to 0. When x is negative 1, you get negative 2 minus 1 is negative 3, so minus 3b, and that means that b is minus 1. And when you sub in x equals a half, that will clear out this. You get 3 equals a times 1.5, so 1.5a, and therefore a is 2. So our partial fractions are 2 over 2x minus 1 minus 1 over x plus 1. And there's our answer. Okay, loads of information now. When chemical A and chemical B are mixed, oxygen is produced. Scientists mix these two chemicals and measure the total volume of oxygen produced over a period of time. The total volume of oxygen produced, V, T hours after the chemicals were mixed, is modelled by this differential equation. Hello, that looks very similar to this. Good to know. Given that exactly 2 hours after the chemicals were mixed, a total of 3 meters cubed of oxygen has been produced, solve the differential equation to show that this is true. Okay, so I need to solve this differential equation. So that is dv by dt equals 3v over 2t minus 1, t plus 1. Okay, so this is going to involve separating variables. If I divide by v, I've got my v's on one side, and I've got my t's on the other. And this is the point to spot that what we have on the right-hand side is just the thing which I've just split into partial fractions. That's useful because I'm about to do some integration. If I integrate the left-hand side with respect to t, I get 1 over v. Now it's this times dt, and the dt's cancel, so we get dv. And if I integrate this with respect to t, I can use my partial fractions. 2 over 2t minus 1 minus 1 over t plus 1 dt. And this is all now doable. So on the left-hand side, it's just ln v. And on the right, it's, okay, integral of this. Well, it's actually just ln of 2t minus 1, because when you differentiate that, you get 1 over 2t minus 1 multiplied by the derivative of this, which is 2. And this one is just minus ln of t plus 1. And then don't forget the plus c. All right, we need to show that this is true. So it looks like expressing this in the form v equals would be useful. First thing I'm going to do, though, is just combine these two logs. So using log laws, I know that's the same as ln 2t minus 1 over t plus 1, and I've got a plus c here. E to the power of both sides gives me v on the left. On the right, when I do e to the power of all of this, I get e to the power of this stuff times e to the power of this stuff. E to the power of this stuff is 2t minus 1 over t plus 1. E to the power of c is just an arbitrary constant a. Okay, we're nearly there. We can just use the conditions they gave us, which is that exactly 2 hours after the chemicals were mixed, so when t equals 2, v is 3. So v equals 3 when t is 2. 2 times 2 minus 1 is 3. 2 plus 1 is 3. That means that a must equal 3 because that's 1. So a equals 3. Let's just check that's what we wanted to show. Yes, there's the 3 there. So we have successfully shown that v is 3 times 2t minus 1 all over t plus 1. Part C. Okay, we've solved that. Okay, the scientists noticed that there was a time delay between the chemicals being mixed and oxygen being produced. There was a limit to the total volume of oxygen produced. Deduce from the model the time delay, giving your answer in minutes, and the limit, giving your answer in meters cubed. So what is this time delay? So for some reason, no oxygen was produced for a certain amount of time. Now, thinking about this graph, the graph of this, we can notice that when t is a half, we get 0 up at the top. Now, when t is less than a half, we get a negative here. Now, you can't have a negative volume of gas. So it must mean that nothing happened until t equals a half. And after t equals a half, that's when this becomes positive and that's when you see gas. So I think that means that the time delay is going to be t equals a half, which is 30 minutes. Now, the limit, giving your answer in meters cubed. So this should just reach some kind of asymptotic limit. Let's just think about what that is. So let's just do each of those things in turn. So the time delay is 30 minutes, because that's when it becomes positive for the first time. And then the limit, well, imagine t gets very, very, very large. As t gets very, very large, we can say this, as t tends to infinity, this here is going to start looking a lot like 3 times 2t over t. Why is that? Well, that negative 1 compared to 2t is irrelevant as t becomes huge, and the plus 1 here compared to that t, if it's huge, becomes increasingly irrelevant. What we end up here with is 6. So the limit is 6 meters cubed. You're never going to get more oxygen than that. Question 15. In this question, you must show all your stages of your working. Don't just use a calculator. Okay, given that the first 3 terms of geometric series are 12 cos theta, 5 plus 2 sine theta, and 6 tan theta, show that. Okay, well, a geometric series has the property that the ratio is the same. So to get from here to here, you multiply by some ratio r, and you multiply by the same ratio to get from here to here. That means that 6 tan theta divided by 5 plus 2 sine theta is r, and so is 5 plus 2 sine theta divided by 12 cos theta. So 6 tan theta divided by 5 plus 2 sine theta, that's the common ratio, and so is 5 plus 2 sine theta divided by the previous term. And look, here is an equation, and it's an equation which hopefully will rearrange to this. So let's multiply through by 12 cos theta. 6 times 12 is 72. Tan theta times cos theta is sine theta. Over here we get 5 plus 2 sine theta all squared. That gives 25 plus 20 sine theta plus 4 sine squared theta. Gather everything up on one side, and we've got 4 sine squared theta. 20 minus 72 is minus 52 sine theta, and then plus 25, and that's what we needed to show. Part B. Given that theta is an obtuse angle measured in radians, okay, an obtuse angle in degrees is between 90 and 180. So in radians, it's somewhere between pi over 2 and pi. Solve the equation to find the exact value of theta. Okay, well, I'm going to want to solve this equation. I definitely just do that sort of thing with my calculator. So I can pretty much just go straight from that to solving it. Here's how. So go to Menu, Equation Solver, Polynomial, degree 2, and it's 4x squared. Let x equal sine theta, basically, minus 52x plus 25. And our solutions are 12.5 or a half. So write them both down, 12.5 or half. Now, clearly it's not that. So I'll just say sine theta is not 12.5. It can't be bigger than 1. So we have sine theta equals half. And I want the obtuse value. So the first solution in radians is pi over 6, but that's an acute angle. The obtuse one is pi minus that. Remember that for sine, if you have a first solution here, your second solution is pi minus the first, because if that's your first solution, your second one is pi minus that. So that's 5 pi minus 6. And so therefore theta equals 5 pi over 6. That's the obtuse solution. Okay, show that the sum to infinity of the series can be expressed in this form. Okay, so let's actually work out what this sequence actually is. Now that we know that theta is 5 pi over 6, let's look at what the sequence actually is. It goes 12 cos theta, and the next term was 5 plus 2 sine theta. So the common ratio is just 5 plus 2 sine theta divided by 12 cos theta. So we can just work that out, because 12 cos 5 pi over 6 can be worked out. Making sure my calculator is in radians, we just get 12 cos 5 pi over 6. It's minus 6 root 3. And what about 5 plus 2 sine, not sine theta, sine 5 pi over 6? 2 sine 5 pi over 6 is a half. We knew that. Plus 5 is 6. So that means that the ratio of the geometric sequence is 6 over minus 6 root 3, which is just minus 1 over root 3, or if you like, is minus root 3 over 3. We also need the first term of the sequence. It was this. It's minus 6 over root 3. Now that you've got A and R, the sum to infinity of a geometric sequence with an R value which is between minus 1 and 1, which this is A over 1 minus R. Now, in what form did they want this? They wanted this in the form k 1 minus root 3. So I can rationalize this now. It probably would be okay to just key that into the calculator, but I won't. You know what? It's probably even easier to do the rationalizing if I leave this as 1 plus 1 over root 3, because I can multiply top and bottom by root 3. I get minus 6 times 3, so that's minus 18, over root 3 plus 1. Now we can use standard rationalizing technique of multiplying top and bottom by root 3 minus 1. Now this bit I absolutely would just do in the calculator. No need to scrabble around trying to work that out. So minus 18 over root 3 plus 1 multiplied by root 3 minus 1 over root 3 minus 1. So 9 minus 9 root 3. Okay, a quick look at the form they wanted me to leave my answer in. K, 1 minus root 3. Yeah, good. Our K is just 9, so that's 9, 1 minus root 3. And so just to spell it out, K was 9. Okay, question 16. So figure 6 shows a sketch of the curve C with parametric equations. X is 2 tan t plus 1, and y is 2 sec squared t plus 3, and t is between negative pi over 4 and pi over 3. Line L is normal at the point where t is pi over 4. Using parametric differentiation, show that the equation for L is that. Okay, to find the equation of a normal, you need the gradient and you need the coordinates. Let's start with the coordinates because that's pretty straightforward. I'm just subbing pi equals 4 into this. So when t is pi over 4, x equals 2 tan pi over 4 plus 1. Tan of pi over 4 is 1, so that's just 3. And y is 2 sec squared pi over 4 plus 3. Well, sec squared is 1 over cos squared, so I can just do cos of pi over 4 and square that. So cos of pi over 4, square that, do 1 divided by my answer and times it by 2. So I get 4 for this, plus 3 is 7. All of that can be done with the calculator. So the coordinates are 3 and 7. Now I need the gradient. I need the gradient of the curve, and then I'll take the negative reciprocal of that. So I'm going to differentiate each of these because dy by dx is dy by dt divided by dx by dt. So dy by dt, I need to differentiate 2 sec squared t plus 3. The derivative, well, you know what, I can just write out y. It's 2 of sec t squared plus 3. So differentiate this. Power comes down, 2 sec t, and drops by 1. Multiply by the derivative of sec t, which is sec t tan t. Derivative of 3 is 0, so that's just 4 sec squared t tan t. And then we can say that when t is pi over 4, what is this? Well, dy by dt is, okay, to work that out, I just do cos of pi over 4, square it, and do 1 divided by that. So that's this bit done on my calculator. I've got 2, times that by the 4, I've got 8, times that by tan of pi over 4, which is 1, and we just get 8. Now I'll do the same for the x's. So dx by dt, I'm differentiating 2 tan t, which is 2 tan t plus 1, so that's 2 sec squared t. And then I can say when t equals pi over 4, dx by dt is, and I've already worked this out a bunch of times and yet I still can't remember what the answer is, sec squared of pi over 4 is 2. So 2 sec squared t is 4. Okay, so that means that dy by dx is dy by dt divided by dx by dt, which is 2. We wanted the normal, not the tangent, and so the gradient we want is minus a half. So now I've got my coordinates, 3, 7, and my gradient minus a half. So I can say y minus the y value is the gradient times x minus the x value. Multiply that out, we've got minus a half x plus 3 over 2. So y is minus a half x, and then we've got 1.5 plus 7 is 8.5, or 17 over 2 is how they wrote it. So we're done. That is what we needed to show. Okay, show that all points on C satisfy this equation. So this is basically converting it into Cartesian form. So maybe it's useful to just have these here again. Y is, I'll need to remind myself, so x is 2 tan t plus 1. And y was, and I've forgotten that as well, 2 sec squared t plus 3. So to convert this into Cartesian, I'm going to use the relationship that tan squared t plus 1 equals sec squared t, because I can see sec squared t over here, and I can find tan squared t here, and I can equate them. So let's rearrange this x equation so that it says x minus 1 over 2 equals tan t, and therefore x minus 1 squared over 4 is tan squared t. Rearranging the y's, I get that y minus 3 over 2 is sec squared t. So I can just drop all of this stuff into this equation. Tan squared t is x minus 1 squared over 4 plus 1 equals sec squared t, which is y minus 3 over 2. Now, they wanted a particular form, so they wanted it in the form y equals. So I will just work on this until it says y equals. Double both sides, and I get x minus 1 squared over 2, which is half x minus 1 squared, plus 2 equals y minus 3. And finally, by adding 3 to both sides, I get half of x minus 1 squared plus 5. And that is what we wanted to show. Okay, the straight line with equation y equals minus a half x plus k, where k is a constant, intersects C at 2 distinct points. Find the range of possible values for k. Okay, have a look at this here. So we've got a chunk of a quadratic here. We've just shown that this parametric equation satisfies, all the points in it satisfy this, which is a quadratic. But it's not the full quadratic. It stops here and it starts here. Now, you can see that at the moment, the line that we had, minus a half x plus 17 over 2, only intersected once. Now, we're told that we've got a special line here which intersects at 2 points. So where could it be? Well, it couldn't be up here, right? That's no good. That's only one intersection. It couldn't be down here or up here. That would be no intersections. The only place where it could be is somewhere in here. Okay, badly drawn line, but in that kind of place. So let's think about what the smallest it could be and what's the biggest it could be. Well, the smallest value of k would be where the line just skims past like that. And the biggest it could be would be where it catches the top of that point there. So our job for 5 marks is to find the k value which achieves those two things. So let's find this top one first. That's fairly easy because we actually know that, or we can work out the coordinates of this point. The coordinates of that point is the minimum value, basically, of, well, it's this minimum value of x, given these constraints here. Now, we can see that when t is minus pi over 4, we get an x value of, well, tan of minus pi over 4 is minus 1. 2 times minus 1 plus 1 is minus 1. So the x value here is minus 1. In fact, let's keep track of this. So when t is minus pi over 4, we get x equals minus 1 and y equals, oh, I'll scroll back up, into here. Well, we put negative pi over 4 into there, so we can work out cos of negative pi over 4. I'm working out what sec squared of it is, by the way. 1 divided by that and square it, times it by 2 and add 3. So y is going to be 7. So the coordinates here are negative 1, 7. So what is k if it goes to that point? Remember, y is minus a half x plus k. Well, if we sub this in, we get 7 equals minus a half times minus 1 plus k. So that's a half, subtract that from both sides, k equals 6.5. So when k is 6.5, we just graze the top there and we get 2 intersections. Now the trickier one is, what does k need to be such that we just slide past like that? Well, the feature of that is that the line and the curve has just one solution. It's like a repeated route here. Now it's actually going to be easiest to do this with the quadratic rather than the parametric equation. We can just say, when does this quadratic and this line, when do they have a repeated root? So the quadratic version which satisfied it was half x minus 1 squared plus 5. And we can say that if it just skims the bottom, right, where here's your quadratic and here's your line, then when we set that equal to the line, we should get just one solution, which means the discriminant should be 0. Let's work that out. Let's expand this. We get half x squared minus 2x plus 1 plus 5 equals minus a half x plus k. Expand this, it's a half x squared minus x plus a half plus 5 equals minus a half x plus k. Everything over to one side, half x squared minus a half x minus minus a half x is minus a half x, unless I've done something silly there. Then you've got half plus 5 minus k. So it's plus 11 over 2 minus k. And this is the equation which should have a repeated root, which means that b squared minus 4ac should equal 0. Okay, expand all of this. We get a quarter minus 4 times a half is 2. 11 over 2 minus k equals 0. Let's get this to the other side. Divide both sides by 2. So 1/8 equals 11 over 2 minus k. Add k to both sides. Subtract an eighth from both sides. We get 11 over 2 minus 1/8, which is 43 over 8, which looks wrong, but in fact isn't. Okay, let's just conclude then. What we know is that when k is 43 over 8, we just graze the bottom and get one solution. So we need k to be bigger than that, strictly bigger than that, to get two solutions. And we also know that when k is up to 6.5, we get two solutions. If k is 6.5, we do get two solutions as well. So we can conclude by saying that k needs to be strictly bigger than that, because when it is that, we just got the repeated root, but it's got to be less than or equal to 6.5. That's quite challenging, but if you can do it, you get 5 marks. Hope that was useful. See you soon. Thanks so much for watching. If you found that useful, you might want to check out my website, mathematicswithwoody.com, where I've made a complete online course covering the full A-level math syllabus. For a fraction of the cost of a tutor, you can get over 70 hours of video content, hundreds of quizzes and worksheets, as well as support from me when you get stuck. The first 100 people to use the link in the description will also get 30% off. See you soon.